So if you open the link to the slides, you'll actually be able to click on these. But just so everyone knows, the point of these meetings is to mostly review material in this textbook, which is available for free online. You can there's a couple of PDFs of it with different formatting. And this website also has links to other supplementary material for the course. The topics we have covered in the past include part 1 of the book and part 2 of the book, which begins with tabular methods, which are problems where you can get an exact solution. And then part 2 covers problems where the problem space is too big and you have to use some kind of approximation to get a solution. This is what the book looks like. People, this is just one of the PDFs. You can just download this from the link I showed. And, this is the table of contents of the book. So we have not done part 3 of the book before. There were some meetings that covered part 3, but it's a little more like qualitative. And this is another one of the survey questions. If anyone is interested in actually covering any of these sections in part 3, it's another option. Probably the one that would have the most interest is the applications and case study section, because that does have some interesting problems. But, what we're going to be doing definitely for the first, group of these meetings is going to be the first 4 chapters of the book. And chapter 1, we don't really have to spend much time on. These slides are going to mostly summarize some of the information in chapter 1. There are some exercises in it we could review at the next meeting if people, have a chance to look at them. But I can show what those are. And these are links to other relevant things for the group. So, there's actually, this meeting is listed on 2 different meetup groups. It doesn't really matter which one you join. The discussion thread might be different for both, but that's about it. They both will have the same meeting link. And then this is a link to join the Discord group. And there is an RL Book Club channel in the Discord group. So that's where, like, if I was going to announce something or ask questions about future meetings, I would probably post it there. And it's kind of a new group, so it's not that active, especially in this channel. But if people do have questions, like some of the new people, this is where I would ask people, post questions, and where I'll post announcements for the group. This is a link to the YouTube playlist, which has recordings of the previous meetings. And then I have on GitHub all of the exercise solutions that I've shown in meetings. If you want to actually, there are interactive notebooks. If you want to actually use the notebooks and interact with them, you will need to install the Julia programming language, which you can find at this link. And otherwise, there are static HTML exports of the notebooks, which you can find at this link. But I can just show, here's the YouTube playlist for these meetings. So, eventually I'll be adding the current recordings that we make. You can see, like, the first recording is of chapter 5, and then it goes through chapter 13. And then,
so if
yep,
you need
question?
to do a lab or to just have an enhanced learning, do you need any kind of cloud services or a cloud subscription or something, or where can we do the hands-on?
Oh, I mean, we haven't done anything like that. I guess Evelyn told me that now Google Colab does now support Julia. So we could use that if you wanted to sort of make use of the code that I've already created here. But we haven't done any meetings with sort of like an interactive tool that everyone in the meeting is like interacting with. It's more like, you could use the interactive notebook on your end and then, write your own solutions and then compare the answer to mine. But, it's an option. Like, we could potentially do more stuff, more interactive things in the future.
Okay.
Yeah, it depends on what, exactly you're interested in. At most, like we've gone over exercise solutions, and if you like have your own solutions, we could look at those and compare them to my answers and see. But, you know, I haven't like prepared like a lab, you know, exercise for people to do in that sense. It's more like, you know, the notebooks I've made have like my own interactive tool or like solution that I use to then generate content for the meeting, but that's about it.
Thank you.
But yeah, this is the GitHub page for this. So, and then there's a link here to the static export page, which looks like this. So then there's just links to the different notebooks. If you open them, you know, it'll render the notebook and show the content, but it's not actually interactive. And a lot of these, they do take a bit of time to load in the browser. I mean, so some of them longer than others. The one I just clicked on happens to be a very long, you know, here's like the table of contents. So it's a pretty long notebook. But yeah, like you'll still be able to see the content, just not interact with it there. And then, yeah, here's, you know, the Julia language if you want to download it. Also, Pluto is the package I'm using for the interactive notebook. So here's, you know, plutojl.org is the website for Pluto, but it's just another tool like other than Jupyter for making interactive notebooks. Yeah. So yeah, hopefully everyone that yeah, I see. Okay, plenty of people have access to the slide deck, so that's good. There's also a group of links at the end of the slide deck, so you know you can just save it, and it should be, you know, a useful, you know, static reference for just all the relevant links. Okay, so now I'm going to get a little bit into like the introduction to the topic that is covered in chapter 1. This is, you know, if you want like just one sentence, or at least what Sutton and Barto think is the most important thing to point out when introducing the topic. They say, you know, trial and error search and delayed reward are the two most important distinguishing features of reinforcement learning. Now, the actual like formal name for the problems that we'll be studying are Markov decision processes, often abbreviated as MDPs. And, you know, what defines these problems is that there is a specific state of the environment, which is something which has a well-defined structure. And at any moment in the process, you can, you know, ask what is the current state that I'm in? And it has, you know, a well-defined set of information that constitutes a state. And then there is also an action space, which allows you to take actions in the environment. And the third aspect is that there is some reward signal which helps define what is considered important in the environment. And, you know, like the reward signal is what sort of defines the goal of the problem. And, you know, there is traditional control theory where often we're looking at things in a continuous time, often, you know, a continuous state space. And the goal is to get some, you know, exact solution. And usually in control theory, there is some, you know, like coupled set of dynamical systems equations, and there could be some exact solution that you solve for. These problems are an extension of that into a messy area where you can't get those kind of neat, exact analytical solutions. But the advantage here is that if you're able to frame a problem as a Markov decision process, there are a whole bunch of techniques that you can use to get pretty good solutions and, you know, exact solutions in cases where, you know, how you've defined the MDP actually matches up with the real problem, as opposed to being, you know, some simpler representation of the real problem. Yeah, but the problems we're going to be dealing with often have bizarre, you know, constraints, nonlinear constraints, things that might be easy to write down, but would make it very difficult to actually, you know, calculate an explicit solution with the techniques that are in traditional control theory. Okay, before I show that, I'm just going to show, I had also made these, like, I was experimenting with making some short videos that summarize some of the introductory topics. So here, I have this this tablet. I sometimes use it in meetings, but this is sort of showing some of what I was just discussing. A Markov reward process is a simpler version of the decision process without actions, but what it does have are these states and transitions. And often in the book, there's going to be these diagrams where you have states with these open circles and then some arrow that points to some transition state. And this is all completely abstract, but these problems are then defined by some sort of probability function, which tells you all the probabilities of going from one state to another. And as long as you have that function defined, you can use a lot of techniques to come up with exact solutions. Here, this transition has now continued on to then another state, and this can continue on, for some arbitrary amount of time until, some systems have terminal states, which are in the book. The convention will be to draw them as this, closed square instead of a circle. But the point of a terminal state is that you never leave it. So, whatever process we're in will end at this state. And otherwise, if we're in one of these circle states, there could be some, one or arbitrarily high number of transitions out of it. Where the reward comes into this, because like what I just showed here, there's no, reward signal. It's just a matter of keeping track of what state you're in. So here, if we have one of these problems, what will happen is we'll have a series of these state transitions. And in addition to having a probability of going from one state to another, there will also be some numerical value that is produced on each transition. And, this is totally abstract, but the point of framing the problem like this is that the actual states could represent, any number of arbitrary things like a game board, some sort of data center with utilization on servers, some sort of chemical reaction with temperature and pressure. And the point is that we want to have an understanding of, if we're in a certain state, what kind of reward will we get into the future? And, it might not be obvious what that is, but when we talk about solving these problems, what we mean is, understanding the conditions where we'll get a large amount of future reward. And that's where this, Sutton and Barto sentence about these problems is how, this delayed reward is a characteristic feature of reinforcement learning. I mean, the reward doesn't have to be delayed, but often, we're interested in states far in the future, which will then have transitions that could produce a lot of reward. And, even if the states we're in now are not producing much reward. So is that any questions about this? I mean, I know it's a pretty general overview, but yeah, like a lot of the discussion in this is completely abstract until you actually get to a specific problem. But then the challenge of working with a problem is to, actually take what you care about in your problem and then use that to define the state space and how the transitions work. But once you've done that, then all of the theoretical techniques will work the same on that problem as they would on any other problem. It's just that the states and the rewards are representing different things depending on how you set up the problem. So, this is a diagram from Wikipedia on a Markov decision process. It looks a little different than the diagrams I just showed, but the idea is the same. This diagram actually, the point of it is that this summarizes the entire MDP, meaning like there are 3 states here, and these arrows are showing all of the possible transitions in the problem. So, these, like, if you look at a given state, then like the probability of all the transitions out of it should sum up to 1. I believe here, yeah, like these numbers actually do represent the probabilities, and I guess the rewards are, well, here, these other like squiggly arrows are showing what the rewards signal is for this. So here, there's also these actions, which are in the orange circles. In the book, actions are often shown as these closed black circles. But the point is that it shows from a given state, there are some actions that you can take, and then those actions will take you into some other state with some reward signal. But more formally, there is this probability transition function, which is, you can write it down as a 4-argument function where you have the state you're in, the action you take, and then the transition state that you end up in. Well, actually, yeah, this notation from Wikipedia is a little different from what's in the book, but you have, the actual reward that you get and the transition state, and then the output of the function would be the probability of all of those things happening, right? So we have like, this function here this is the probability of if you had taken this action A, that you would end up in state S prime, starting in state S. But, this is a very small problem. So there's only 3 states in the state space. And then, there's some number of actions. It looks like there's only 2 total actions in this problem. And then, some, reward signal, like the rewards can be, any arbitrary real number. But you should avoid infinite values because that can end up filtering down and screwing up the values of all of the other states in the system. So typically, the rewards will be some finite number, but there's no restriction to being negative or positive or anything. Okay, so I already mentioned a little bit of this, but like the goal throughout the book will be to solve these problems to the extent for a decision process. That means finding an optimal policy where the policy is the thing that actually defines what decisions are made in every state. So there is some policy function, and there you can prove that for any of these problems that an optimal policy exists. And that optimal policy is something that will produce the greatest future rewards, like at any given state that you're in. Following that optimal policy will produce the most future reward. And that is true for every state. So it's truly like a global optimum. And there will be techniques that we'll see throughout the book. In the first 4 chapters, we'll be eventually building up to exact techniques to, if the problem is framed in a certain way, if it's a tabular problem, which is small enough, then we can use a few different techniques to get an exact solution to these problems. And then, once we've applied one of these techniques, we will know what the optimal policy is, and then we can use that policy to interact with the environment. And if we observe that policy in the environment, it should, on average, through multiple interactions with the environment, it will produce the most reward. So, that probability transition function I showed earlier is something where if it's encoded in a certain way in a computer, then it's possible to use that to interact with the environment and get feedback, because, you would then provide whatever state you're in and whatever action you want to take. And then from that, you can get some feedback, both of what state you end up in and what the reward is. And, some of the techniques involve learning from the environment by taking samples as sort of in a sort of simulation style. There are also techniques that sort of would look at this entire function and come up with an exact solution without having to actually go through these states and like have an agent interacting with the environment and getting feedback like that. But for techniques that involve choosing actions and actually moving through the environment, there's always this challenge of deciding, how much do you want to exploit knowledge that of what's already a good policy, and how much do you want to explore what could potentially be better actions. So a lot of especially chapter 2 in the book is very concerned with balancing this, exploitation trade-off. And, but again, there are techniques which essentially will have a guarantee of finding the exact solution without needing to do this. It's just that in order to apply those techniques, we're going to need like as much information as possible about the environment, like the knowledge of this entire diagram. often we don't know what this diagram looks like. We only have the ability to, simulate it in some way. And in those cases, we can't actually compute an exact solution. We have to, estimate things with some sort of Monte Carlo method of sampling from the environment. Yeah, so basically, like, the essential components of all the problems are, in order to apply the techniques of reinforcement learning, we're going to often be talking about, a policy, which again defines how the agent behaves, how it interacts with the environment. The policy itself could be stochastic, meaning that there is some random, there is some probability of taking actions, which is not necessarily one for every state. So you could have, a split between two different actions, or, two or more actions that all had non-zero probability. And then we're always going to be talking about the reward signal, which is what you get back from the environment when you make these transitions. And then for part one of the book, we are going to eventually be talking about something called the value function. And the value function is an attempt to quantify how valuable is it to be in a given state. And by value, we mean, what do we expect from future reward from this state? And there's value functions that compute the value of states. There's also value functions that compute the value of state action pairs, because for, MDPs, there are both states and actions. And, whether we use one or the other depends on what technique that we're going to implement to solve the problem. But, eventually we will work with both types of value functions. And there's also other techniques that involve planning and decision making, which, there's already a video of that in the playlist. I believe it's the recording of chapter 8 from the book. Now, in order for these problems to be well posed, the state has to contain all of the relevant information for the environment. So, and that's because when we write down what the state is and what the action is, there should be a well-defined probability of all of the transitions that happen. If there's other information, like if something is changing over time and it's not being captured in the state space, then you may have a situation where those probabilities are changing over time. And that would not be a well-defined MDP. It would violate this Markov property. Now, there could be information which is not available to the agent, as long as that information isn't changing through time in some way that would violate the Markov property. So, there could be some unknown thing which happens from a state, and if it's not available in the state, it would end up looking to the agent like there was just some other random probability of these transitions, right? It would just be incorporated into the transitions. And I can kind of, here, I'll show an example of this. And this is from this notebook, which summarizes all of the sections in part one of the book. But this is showing a common model for MDPs, which we use, which is this Gridworld environment, where the states are just what square you are in the grid. It's a simple thing to visualize, but you can also think of it as these grid squares could be abstracted to other things. But in this case, there are 4 actions, which I'm showing here. The actions are just what direction you're moving in the grid. And there's this windy grid world example in the book where this is showing, so if I take the right action, this blue square is showing what state I'm in. And then with the right arrow action, this is like a grid world where there's some, wind, which the purpose of the wind is to perturb the movement of the agent. So in this case, it pushes the agent up 1 square when it attempts to go to the right. So instead of going directly to the right, it goes 1 to the right and 1 up, right? But then you could imagine this being a stochastic environment where, the wind you could end up in any one of these 3 squares with equal probability. So here there's a 1/3 chance of going directly right, going up 1, or going up 2. And that it may be the case that with more information about this, like maybe there's some, values fluctuating in time or exactly how the wind, hits you, that you would know exactly which of these transitions would occur. But we can also model the problem as whatever those forces are, they're not known to the agent, but they end up producing this 1/3 probability anyway. So this is still a valid MDP and a stochastic one because these probabilities are not going to change throughout. If you had a different problem where the wind values were like going up over time by some constant amount, then these probabilities would not be valid because if you looked at the problem at some point in the future, they would be different. So it's okay for information to be, hidden from you that isn't captured in the state, as long as it, it still has this Markov property. But you can show when we talk about like solving these problems, here is, so like eventually what we're going to build up to is like a preview of, but by the end of chapter 4, you have a number of techniques available. This is one technique where you define the problem in this way, and then you start out with some random policy where the agent is just moving randomly. And then there's a sequence of improvements that are made where after each step, you get this change in what the policy is doing. And eventually you settle on the optimal policy, which is being shown here, where the arrows are showing what is the optimal action to take from every square. And then these values are showing, what the expected reward value is in the future. In this case, there is some goal state that you're trying to reach. So depending on where you are in the grid, you would go for, one goal or the other, and you get some reward for reaching the goal. But you can see that because this is showing the value function, when we start out, the values are low. So here it's like, 0.06, 0.093. This green square is the starting state that you always start in. And then by the time we reach the optimal policy, we now have improved this to the highest possible value, 0.45. And then all of the values throughout the grid will be higher than they would be for any other policy. And that's what makes this the optimal policy. So that's what we mean by, solving this problem. In this case, this would be constitute the solution for this grid world setup. So the rest of chapter 1, it does talk about this tic-tac-toe example, which ends up being the subject of a few of the exercise questions. And why don't I actually show this part of the chapter. So this is the introduction, and I do recommend actually reading the introduction if you haven't before. It's like a pretty good summary of the topic. I don't think it would be like a waste of time to read it even after looking at this slideshow. So talked about this, and then section 1.5 talks about this tic-tac-toe example. And I think for the next meeting, if people are interested in reading through this section, it then forms the basis of these exercises. So there are 5 of them. They're all qualitative exercises. You don't have to like actually really do any math. They are just, ways to help you think about the problem, and, then you can see how your intuition compares to what you would actually do to solve this problem. And, I'm not going to bother going through it now because I think it won't really, like, none of these exercises will make sense if you haven't read the section yourself. But it is, I think these are worthwhile to go over. I also do have my own write-up of these exercise solutions, which you can find in that GitHub link, but you probably shouldn't read my answers if you're interested in thinking about the problems on your own. One of the questions is actually, discussing playing a random opponent in tic-tac-toe, and what would happen, and yeah, this idea of symmetries in the game. I can show, if we actually talk about those exercises, we can also go a little bit more over this notebook, which has an actual implementation of this tic-tac-toe problem. And in this case, this is something you can look at this and how it's coded, and by the end of the book, or even after maybe just part one of the book, this would be something you could apply all the techniques to computing something like this. But what's being shown here is the optimal policy against a random opponent. So in this case, like the starting player is the X player. So the green squares are showing these 4 actions are all equally good for the X player, which also makes sense because in this case, like the board is completely symmetric. So you would expect that the optimal actions would, satisfy this board symmetry, because it wouldn't make sense if this was an optimal action and this wasn't, because if you rotate the board or do a mirror reflection of the board, the action should be identical. But then as you play here, like if I actually take this optimal action, then this is now showing the optimal action for the O player, which is, to play in the center of the board. If you played in any other square, leave, and then if I followed this, then any of these actions should eventually lead to a win for the X player. Yeah, because now even if O blocks this is still a win for the X player. So, and then this is showing here the value estimate for each player. Right. So the reason why I'm here in this problem, you get a reward of 1 for winning the game, at least for the X player. So you could see that from this value function, you can see that the optimal policy against a random opponent has a 98.8% chance of winning. And of course, in tic-tac-toe, if you're playing an optimal opponent, you would expect to draw every game. So clearly, against a random opponent, you have a much higher chance of winning. And the optimal policy could actually be somewhat different from the optimal policy against an optimal player. But, again, maybe next time or in one of the future meetings, we can look more closely at this problem and how the policy compares as you play different types of opponents. But for now, I think, yeah. So for what would be good to review for next time, I think it's this section 1.5 in the introduction. And I don't think it would take too long to go through these exercise solutions. And then chapter 2 is a completely different topic on these multi-armed bandits. So I think for the next meeting, we would begin chapter 2, at least after going over some of the exercise solutions in chapter 1. But, you won't have to worry about actually reviewing anything in chapter 2, because it is a completely different topic. It's actually designed to introduce the idea of sampling and estimating values from exploration and balancing exploration and exploitation. And it's really more of trying to build up some foundational techniques that will be useful in the later chapters. It doesn't actually cover solving Markov decision processes, which will happen in chapters 3 and 4. So, and then the final slide here I have are some of the links I showed earlier, but also additional links. Like there is a Google Drive folder also from Sutton and Barto, which has a bunch of other teaching material. It's not like particularly well organized, so it's probably would be hard to find exactly what you're looking for there, but it is available if you're interested. There are also other videos, other YouTube playlists for other versions of this course. And then also Max, he had done some solutions, so this is a link to his GitHub page with that. My solutions, again, are here. And there's also there's a Gridworld demo, which does require Python, but from Richard Sutton, and that's at this Google Drive link. So yeah, hopefully, if anyone's left in the meeting and didn't have access to the link with the slides, please, let me know in the meeting chat so I can send it, because, I don't think people are going to be actually typing this manually into a web browser. All of these links. But are there any questions from anyone, or would anyone like to see one of the previous slides or anything I showed? And
Jason, I got a question.
Uh-huh.
So I was wondering from like a practical perspective, in terms of like, I'm sure there must be a pretty big spectrum in terms of simpler problem spaces and much more complicated problem spaces. But generally speaking, like how much time or compute does it take to actually train a reasonably decent reinforcement algorithm so that it does a decent job?
So I mentioned, so what I'm showing here, for example, like this is just a complete toy problem, but you could use this as an analog for any problem, because you
Sure.
could imagine the states. Like this is actually being solved in real time, like in this notebook. So it's computing this in, I don't know, some like 1 millisecond or something. This is what would be called like a tabular problem. There's another example which is probably very applicable to a lot of business cases, actually, I think in chapter 4, where you could imagine like a problem where you have like inventory and some model of customer behavior. And for a problem like that, the state space may not be that big, like depending on how much your inventory can range, or you could bucket it. And if, depending on how big it is, like even up to maybe like 100,000 states, you could apply one of these exact solution techniques and it wouldn't take very long at all. And in that case, you wouldn't have to worry about it being, how good the solution is, because if you frame the problem in that way, you can guarantee an exact solution. There are other problems where you may not be able to define like all the probabilities. There's actually, I think if you look at the video of chapter 5, that looks at the blackjack example. And that's a good example of a problem where you sample from the environment, because it's actually very hard to write down what all the probabilities are, but it's very easy to write something that can simulate the environment. And in that case, you're collecting samples, you're interacting, and the number of steps you need to solve the problem, you don't really know ahead of time. All you know is that eventually you'll converge to the solution, but there are heuristics. You can keep track of some error values as you're training it to see how close you are, how much the solution is changing. But I would say it all depends on how big the state space is and how big the action space is. So if you're talking about, a few thousand states, usually the actions are more limited in these problems. Like often there could only be like 2 actions, or, I mean, if you really have like thousands of actions, you start, like the number of state action pairs is relevant to the problem size. So if you have like 10,000 states and 1,000 actions, it's a much harder problem than if there's only 2 actions. But
Got
it's
it.
really only when you get into like, the millions or tens of millions of states do you start having to do things where you can't get an exact solution. So yeah, I don't know if it also depends on how, if you're sampling and you have a simulator, it depends on how fast your simulator is. So, because you're going to have to use that to collect samples. So if you have like a really slow simulator, then yeah, it's going to take a very long time to solve the problem, but if you have something that you can, write in code, like, I mean, like worst case scenario is you actually have to interact with a real system in real time, like a physical system. And then you're very limited in how quickly you can collect samples. But if you can, simulate it in a computer and have a very fast running one, then you can collect samples very quickly. And, it wouldn't take that long to do, but if you're comparing it to like supervised learning, where you have like a big data set. Here, like there's no data set. Your data set would sort of formed in real time by interacting with the environment. So, you could imagine like if you have a sense of how big the problem has to get before it's not feasible for supervised learning, you can sort of, if you translate that into like number of examples, you can compare that to like, I have this simulator, here's how quickly it runs one step. That's, if I need like 100 million steps to solve this problem, you can estimate, how long it would take to collect enough data to do that.
That makes sense. Thank you.
Mm-hmm. Yeah. Any other questions or requests for future meetings? Again, I mentioned like what the plan is probably going to be for the next meeting, which is beginning on chapter 2, but before that, going over this section 1.5 and the exercises in 1.5. So if people are interested, you can look at them ahead of time, because I will be actually going over, answers for that. So if you see the answers before you've actually tried to do them yourself, it may not be, that useful.